All right, hello everybody. So today we're going to be talking about U-Substitution. All right, so the first thing to talk about is the chain rule. So that's something that we talked about in Calculus 1. So we'd like to talk about that again here. Um, so let's say we have a function f of x equals 3x squared minus 12x to the power of 4. And we want to take the derivative of this function. Okay. So what we did here in calculus 1 was we said, well, we have an inside function and an outside function. So here, this is our inside function. Write this here, this is our inside function. And this is our outside. Our outside function is going to be this power here. This is going to be x to the fourth. Okay. So the way that we took the derivative of this type of function was we said that f prime of x equals, we said it was going to be the derivative of the outside function. So the outside function is x to the fourth. So we'll go ahead and say it's going to be 4 times the inside function to the third, right? That's the derivative. And here we plug in the inside function. And what do we multiply this by? Well, it turns out what we multiply this by is going to be the derivative of the inside function. Okay. So this is going to be our derivative, and now we just need to solve for the derivative of the inside function. So that's going to be 4 times 3x squared minus 12x to the power of 3 times, then again, whenever we're taking our derivatives, so this is how I found the derivative here. We have x to the fourth. We use the power rule to say that the derivative of this is going to be we take out the exponent and we reduce the exponent by 1. That's how I took the derivative away. But here we want to take the derivative of this function, so we take the derivative of each part. So the derivative of 3x squared, we'd say, well, the derivative of x squared, we take out the exponent, write that as the coefficient, so we're going to have 3 times 2 times, we reduce the exponent by 1. That's right? So it's the same thing I did up here. I took out the exponent as the coefficient and then rewrote that exponent as the original one minus 1. And then the same thing here. You take out the 2 and then you reduce the 2 by 1 to get 1. X to the 1 is just x. Okay. We do the same thing for the second term. So the derivative of 12x, that would be minus 12. The derivative of negative 12x would be negative 12. Right? Because the derivative of x is going to be 1. Right? So you just use the same logic. Derivative of x would be 1. Right? So this is how we would get the derivative using what we call the chain rule. So I would say here that chain rule said whenever we had f of g of x and we take its derivative, then it's going to be the derivative of the outside function. Sorry, I misread that. There's some eraser. So it's the derivative of the outside function, you plug in the inside function, and you multiply by the derivative of the inside function. Okay. So this is going to be our derivative. This is what we call the chain. So let me write that here. So this was the chain. So that's what we used in the above example to get that derivative. Okay. So that's our chain rule. And we want to ask, how can we actually reverse this process? So we actually learned something in Calculus 1 that allowed us to reverse the process. So we called it U-substitution, which is what I'm talking about here. So let's say that we have the integral of 4 times 3x squared minus 12x cubed times, so this was set, this was a set, times 6x minus 12. right? So we learned in calculus 1 that the derivative and the integral, they were opposite operations. So whenever we take the integral of this thing, we should get back to what we started with before we took the derivative, right? If you take the integral of the derivative, you should get back to the original function. So we see here that I've just rewritten this exact same answer that we had. So whenever we take the integral, we want to find a way to get back to what we started with. So that's what we do with U-substitution. So with U-substitution, the first step here, I'll say here's step 1. Set U equal to the inside function. Right, so we're going to set U equal to be the inside function. So I'll go ahead and say, well, what's the inside function here? Well, you've got to determine what's the inside function, what's the outside function. But if we've got something inside of a power, I'd say that's probably the inside function. So I'm going to go ahead and say U equals the 3x squared minus 12x. So that's our U. Okay. And then our step 2. Step 2 is to take the derivative of U. Okay. So our second step is to take the derivative of this U. So we can say here the U. So the derivative, we'll say du equals, so strictly speaking, we'll say the derivative of du, we said was du by dx. And the derivative of the right side, again, doing the same thing we did initially, is going to be 6x minus 12. So take the derivative of both sides, that's what you get. Okay. And then we move the dx to the other side, so du equals 6x minus 12 times dx. So moving the dx to the other side. So in the next section, in the next section, what I'm going to be doing is actually just skipping this initial step, or sorry, this middle step. So I'm going to go straight from this u to this next step. But know that this is what I'm doing. I'm taking the derivative of both sides and moving the dx to the other side. But here I'll just go from this step to this step. That's what's going to be in the next. But that's how we're going to find this derivative of u. And then now we need to, our next goal is to rewrite the whole integral in terms of. So step 3 is going to be to rewrite the integral in terms of u. Okay, so we can say here we've got a u, we've got a du, and now we can rewrite our original integral. So our integral of 4 times 3x squared minus 12x cubed times 6x minus 12 dx. So this is our integral. And if we replace everything with u's, then what we're doing is we have 4 times, we said this was our inside function. Inside function was this part. So we've got u to the power of 3. And the 6x minus 12 dx, this part here, we said that this part we can replace with du. Okay. So we're going to replace that part with du. So du. Right. So I'll say here, it's very important to write this dx here, because otherwise it's not going to make much sense. Because you need to be replacing this dx with a du. Whenever you write an integral, you need to know what you're integrating with respect to. So you always need a dx or a du. And here, since our integrand, right, this part was called the integrand inside of the integral. Since our integrand is in terms of u, that means that our integral should also be in terms of u. So we should be integrating with respect to u. Okay, so now we've rewritten everything in terms of u. Now we can actually take our integral. Okay. So if we take our integral, we know, well, the integral of this we said should be 4 times the integral of u to some power, let's say this is u to the third power, then what we're going to do is we're going to increase the power by 1 and divide by the same number, right? So I just increase this 3 to a 4, and we divide it by the same number. And remember, for all integrals, we want to add our plus c. Okay, so it might have been a while since some of you have taken Calc 1, but this is how we do it. We just increase the number by 1, and we divide by the same number. Okay, so this is our integral. 4 divided by 4, this is 1. And the last step is to replace our u's. So u to the fourth, we can replace that with whatever we said u to. So we can replace that with 3x squared minus 12x to the power of 4 plus c. And this would be our final answer, right? So I didn't write it out here, but step 4 would be replacing u in your original. So you replace all the u's into something in terms of x. Okay. But now we want to see, well, that's just one example. How do we do this in a bunch of examples? So that's what I'm going to run through now. So let's flip this to the other side. Doing this with one hand is difficult. Okay. So let's just do another example here. So let's say that we have the integral of sine squared theta times cosine theta d theta. Okay. So this is our integral. Maybe I'll clean this up a little bit. But this is our integral. And again, we can't solve this integral normally. So if we can avoid using U-substitution, we'll certainly try to do that. But we can't actually do that here, right? Because we don't know how to take the integral of sine squared theta cosine theta. So we need to rewrite that somehow. So again, we want to look for an inside function and an outside function. And as I said earlier, if you've got some power, something raised to some power, the inside part there is probably the inside function. So as you might be able to guess here, the inside function, actually let me erase those. The inside function, which we're setting equal to u in our step 1, is going to be sine theta. Right? Because that's inside of the power. Sine is being squared. Sine theta is being squared. So again, we're doing a U-substitution problem. So we want to take the derivative of u. Or sorry, we take the derivative of both sides of the equation. So the derivative of the left side we write as du by dx, because d by dx is the derivative. We multiply by u. Derivative of u, not multiplying by u, but this is what it looks like whenever you take the derivative of u. So we take the derivative of the left, and if we do something to the left side of the equation, we have to do the same thing to the right side. So we took the derivative of the left side, now we take the derivative of the right side. The derivative is sine of theta. I'm sorry, I should have written theta here. We're taking the derivative with respect to theta, not x. You have to be careful there, because this is a theta, not an x. So the derivative of the left with respect to theta, and then the derivative of the right with respect to theta. And the derivative of the right side with respect to theta, the derivative of the sine, if you remember, is actually going to be cosine. So the derivative of this would be cosine theta. Okay. And again, as we did earlier, I'm going to move the d theta to the other side. So du equals cosine theta d theta. And remember that d theta is very important to have there. Okay. Because it tells you what you're doing in your original problem. So now this is our scratch work. I just like to write this as our scratch work. And now we can actually rewrite. So our next step was to rewrite the original integral in terms of u. So we can write here, this is the integral of, well, we said that this first part, the sine theta, and here we said that that was equal to u. So we'll say that this is u, and we said it's raised to the second power. So it's u squared. And the second part here, this cosine theta d theta, well, that matches up exactly with what we said was du. So again, remembering this d theta, this cosine theta d theta turns into du. This is du. So now I've got the integral of u squared du. Looks like the orange doesn't show up super well. Maybe I'll use a different color. But we've got the integral of u squared du, and now we can just solve this integral. So again, the integral of u squared, we add 1 to the exponent, we get u cubed over the same number, 3, and plus the constant c. Right, we always have to add the constant c whenever we have an indefinite integral, meaning we don't have the limits of integration. Okay. And now we just plug in back what u was equal to. So u was equal to sine theta. So our answer here is going to be sine theta to the power of 3. Let me rewrite this. Sine theta cubed over 3 plus c, which is the same thing as sine cubed theta over 3 plus c, right? So both of these mean the same thing. It's just some people write it a bit differently. This is how it's most commonly written, but you could alternatively write it the first way. It means the same thing. Okay, so that was example 1. Let's move on to example 2. Let's say here example 2 is going to be the integral of x to the 4th over x to the 5th plus 1 dx. Okay, so this is the integral that we're trying to take. And here we're looking for an inside function and an outside function. So you might want to ask yourself, what is the inside function going to be here? And for all my questions, you're more than welcome to pause the video to try to answer them yourselves. But we have 2 choices, it looks like, right? We could either say u equals x to the 4th or u equals x to the 5th plus 1. And we always want to set u to be equal to the thing where if we take the derivative of it, we actually see the derivative, or at least part of the derivative, in the original equation. So if we set u to be the bottom part, well, the derivative of x to the 5th plus 1 is 5x to the 4th. We already see an x to the 4th up here. So that gives us the clue that our u should actually be the denominator, because now the derivative of the denominator looks similar to the numerator, something we already have in our integral. So as I said there, our u is going to be x to the 5th plus 1, right? And again, we take the derivative of both sides. Du by dx is 5x to the 4th, and then move the dx to the other side. Du equals 5x to the 4th dx. Okay, but now we run into a little bit of an issue, because if we look at the integral that we have, up here we have x to the 4th dx, but down here we have 5x to the 4th dx. So we need to actually fix that. So the way we fix that is by saying, well, down here we have 5x to the 4th dx, up here it's different. So we want what we have here to match what we have at the top. So we want to do something to both sides here to get it to match. You can ask yourself, what should we do to both sides? And the answer there would be, we need to divide both sides by 5. Because if we do that, we get 1/5 du equals x to the 4th dx. Okay, now this x to the 4th dx matches what we have up there, which is exactly what we were looking for. So that was our scratch work. And now we can just solve our integral by first substituting in what u is equal to. So we said the denominator was u, so we've got 1 over u times this x to the 4th dx. We said we can replace with 1/5 du. So we're going to do that. 1/5 du. So the x to the 4th dx disappears, and we replace it with that. Okay, now we can pull out the 1/5. 1/5 times the integral of 1 over u du. And you can ask yourself, what's the integral of 1 over u? And the answer there would be the natural log of the absolute value of u plus c. Right? So that's another integral that you just have to remember. It's the integral of 1 over u, and that would be natural log of the absolute value of u. And the last step here, you can ask yourself, what's the last step that we forgot to do? The last step here is that we need to plug in exactly what u is equal to. So we've got 1/5 natural log of the absolute value of u. We already said what u was. So x to the 5th plus 1. Let's write this plus it. Okay. Now be our answer there. So probably blocking, but that's our answer there. Okay. So now we can move on to the third example. Let's do that. Okay. So the third example is going to say the integral from 1 to 2 of e to the x, sorry, e to the 1 over x over x squared dx. Okay, so this is our integral. And once again, we need to find an inside function and an outside. But first, let me just go ahead and rewrite this thing. So we can rewrite this as the integral from 1 to 2 of e to the 1 over x times 1 over x squared dx. Okay. And sometimes whenever you have these fractions inside of the problem, it makes it a little bit difficult for us to actually solve the problem. So we saw whenever we were trying to take derivatives initially, that whenever we have something like 1 over x, it's hard to take the derivative of that. So what we do is we rewrite it. And the way we rewrite it is with a negative exponent. So if you ever have an x variable in the denominator, you can pull it into the numerator by making the exponent negative. So we can rewrite this as the integral from 1 to 2 of e to the 1 over x becomes x to the negative 1, and 1 over x squared becomes x to the negative 2 dx. Right, so this initial problem looked a little bit scary, but now that we've rewritten it, we can just solve it using U-substitution like we solve the other problems. So that's our goal here. So we want to say u equal to the inside function. So we saw here in the previous problem, well, sorry, not the previous problem, one before that, that whenever we have something inside of an exponent, that's probably going to be the inside function. And in this case, we have something that is actually the exponent. So we got some function in the exponent. So that's actually probably also. So we're going to say our inside function is going to be x to the negative 1, because that's the power that e is raised to. So if that's our inside function, now we've got to take the derivative of both sides. So we've got du equals, so du by dx equals the derivative of the right side. So we pull out the exponent and we reduce the exponent by 1 to get negative 2. Okay. Now we move the dx to the other side. So du equals negative x sub negative 2 dx. Okay. And now we have to analyze, well, is this actually the same thing that we have up here? And the answer is no, because up here we have x to the negative 2 dx. Down here, this one is negative. So we need to multiply both sides by negative 1 to get negative du equals x to the negative 2 dx. Now what we have here matches. But in all these problems where we've got limits on the integration and we're doing U-substitution, there's actually an extra step that we haven't had to do for the other problems that we've done today. And the extra step is that we need to change the limits of integration. So there's actually two ways of doing these U-substitution problems. But the way I'm going to teach today is that we need to change the limits of integration. So whenever we set u equal to this, we just need to plug in both of these numbers. So here we're going to take u of 1 and u of 2, meaning we're going to plug in 1 into u, and we're going to plug in 2 into u. So u is x to the negative 1, which is the same thing as 1 over x. So this is 1 over 1, which is 1. This thing is 1 over 2. Right, because u is 1 over x. X to the negative 1 is the same thing as 1 over x. So I'm just plugging in 1. So this gives us our limits, right? So we just rewrite our limits. So sometimes it turns out that the bottom one's actually bigger than the one at the top. So u of one, the bottom one, becomes one, and the top limit becomes 1/2. And that still makes sense. You're still allowed to do that. It just looks a little bit weird. And then now you just have to rewrite your whole integral in terms of u. So our exponent we said was u. And we said that x to the negative 2 dx is the same thing as negative du. So I'm going to say times -1 du. Okay. Now we're almost done with our problem. So we've got to take out, I'm going to factor out our constant. So we've got negative times the integral from 1 to 1/2 of e to the u du. And now we're going to have to just solve our integral. Right? So the integral of e to the u. Remember, the derivative of e to the u was e to the u. So the integral of e to the u should also be e to the u, right? Because the integral undoes with the derivative. So this is going to be negative times e to the u from 1, 1. Okay. So this is what we got here, and now we just need to plug in our numbers. Remember, for a definite integral, we just need to plug in the top number and subtract when we plug in the bottom. So we're going to get negative of e to the 1/2 minus e to the power of 1, which is going to be the same thing as if you multiply this by -1, you're going to get e minus e to the 1/2. And that would be our answer. Okay. So that's how we would do one of those types of problems. And I think I'll just do one last type of problem in this section. And let me pick which one I want to do here. Let's do this one. So it's probably been a while since a lot of you taken trigonometry, so I figure it's probably good to do a few more trigonometry problems, since trigonometry is very heavily used in calculus. But okay. So let's say we have the integral of theta squared secant squared of theta cubed d theta. Okay. So this is the integral that we're trying to take. And now we've again got to identify an inside function and an outside function. And well, if you've got some weird angle inside of the trigonometric function, it's probably your inside. So I'm going to say here, probably going to have u equals theta cubed. And the other way of seeing that is if we take the derivative of that, then some version of the derivative appears here, right? Because the derivative is 3 theta squared. We already have a theta squared in our integral. So it would make sense if u is equal to theta cubed. Okay, so this is equal to u. And let's say our du by d theta is going to be the derivative of the right side, which again I said was 3 theta squared. And again, we want to make sure this matches, or let's first move d theta to the other side. And now we want to make sure this matches what we have up top. So up top we have theta squared d theta, but down here we have 3 theta squared d theta. So we need to rewrite that. So divide by 3 on both sides. Okay, so this is what we got here. And now we can actually rewrite our original integral in terms of u. So if we want to do that, we can say that it's equal to the integral secant squared of theta cubed, theta squared, d theta. Okay. So we've rewritten our original integral as this. So the reason I actually rewrote it like this is just because we can see that the second part is the same thing as 1/3 du. And this first part we said was same thing, secant squared of. Right. That's why I rewrote it like that. You don't have to rewrite it like that. It's just kind of helpful to see what's going on. So if we just plug those in, then we're going to get the integral of secant squared of u times 1/3 d. Okay. And now we take out our 1/3, so we're going to get 1/3 times the integral of secant squared u d. And now the integral of secant squared is the same thing as tangent, so we're going to get 1/3 of tangent of u plus. Right, because the derivative of tangent is secant squared, so the integral of secant squared should get you back to tangent. And now, as we said, the last step of the problem is that we've got to plug in what u is equal to. We're going to plug in, so it's going to be 1/3 tangent of u, we said was theta cubed, plus 6. Okay. So this is going to be our answer. Okay. Now I've got a bunch more examples prepared, but I don't think I'm going to go through them all. So instead, what I'm instead what I'm going to do is I'm just going to write them down. So these are just going to be exercises. You don't have to do these, but I'd recommend doing them just to make sure that you understand what's going on here. Okay, so our first exercise is going to be the integral of x squared times e to the x cubed minus 5 dx. And the answer there is going to be 1/3 e. Sorry, this is a little bit sloppy. You're going to be 1/3 e to the power of x cubed minus 5 plus c. Our second exercise is going to be the integral from pi over 2 pi of sine theta cosine cube theta d theta. And our answer here is going to be negative 1/4. Right, so if you're getting the wrong answer there, make sure that you're actually changing the limits in terms of u. So you just have to plug these limits into u to figure out what u is equal to. And then part C is going to be the integral of 12x cubed minus 10x over 3x to the 4th minus 5x squared dx. This is going to be equal to natural log the absolute value of 3x to the 4th minus 5x squared plus c. And our last one here, part D, is the integral of 4 times 4x minus 1 to the power of 7 dx. And the answer there should be 4x minus 1 to the power of 8 over 8 plus c. Okay. So again, those you don't have to do, but if you'd like some extra exercises, I'd certainly recommend doing this. Okay, we'll go ahead and end that there.